with starting our next unit, oscillatory motion and mechanical waves. We're going to start by discussing the simple pendulum, and that's part of oscillatory motion. What is oscillatory motion? It's motion that oscillates, that goes back and forth and like repeats itself over and over and over. Okay, so obviously a pendulum does that because what is it? It's a mass on the end of a string that's just going back and forth and back and forth. So we call that small object on the end of the string a bob, and it's suspended from the end of a lightweight cord, so then the mass of the cord then doesn't affect the way that the bob is going back and forth and back and forth and back and forth. So this is considered to be simple harmonic motion. So again, what is simple harmonic motion? We're going to get into it in more depth in the next lesson, but all you need to know about simple harmonic motion is it's just motion that goes back and forth, back and forth, back and forth. It's motion that repeats itself, okay? So all circular motion is actually simple harmonic motion, right? If it's going around and around and around and around, it's repeating itself continuously. So again, we can, what am I trying to say? We can treat a pendulum like simple harmonic motion if we have the following assumptions. The cord doesn't stretch, okay, because then that gives us some elastic energy as well, and then we're not in just nice simple harmonic motion. The mass of the cord can be ignored relative to the bob, so the bob has to be much heavier than the cord. Okay, so you can't have a really heavy cord with a really, really light thing on the end. That's not really a pendulum. Negligible friction, so not a ton of air resistance. And angular displacement is small. Okay, so when I take a bob, so if here's my, pendulum usually, and then the things on the end, and then I lift it up, this angle has to be 20 degrees or less for it to be simple harmonic motion. If you lift it up too high, then we'll have more air resistance, and so then there'll be too much friction, and we will no longer have the negligible friction thing happening. So of course it needs to be a smaller angular displacement if we want to be able to ignore friction. Okay, so let's just go over what's happening at different parts of a pendulum. So when it's at highest height, and we did actually go over this and when we were looking at conservation of energy, but at its highest height, it has to change direction. So my velocity is 0, okay? So we have force of gravity, of course, acting straight down, but the fact is that since it's kind of not at a bit of an angle, you actually have this force here that is actually trying to push it down. Okay, because of course we always want to look at stuff that's parallel and perpendicular. Okay, so we can see that there's actually some force parallel to the pendulum and how it is right now, and that's what's pulling it downwards. Okay, at its bottom, when it's completely reached the bottom of the swing right here, that's when its velocity is at its maximum. Okay, and that's when all potential energy has been changed to 0 or reduced to 0 because all the potential energy is gone because it's gone down its full height. Okay, so here we don't measure with like its height off the ground. We measure its height with compared to its highest height when the string is completely stretched out and fully headed downwards or looking like it's going downwards. Okay, and then of course at the other side, then we have something like this. We have basically the same thing that was happening at the other highest side on the right, except for now it's on the left, so the forces are all in the opposite direction. But again, at its highest height, we always know that we are going to have a velocity of 0 just for a split second, right? Because it's changing direction, so we know to change directions it has to reach a velocity of 0 really, really quickly. And of course, force of gravity is straight down, but we need to look at things in terms of parallel and perpendicular. And so we do have a component of that force that is parallel that is going to bring that pendulum back down. Okay? And that's that. So that's how a pendulum works. Now, what do we care about when we are looking at something like simple harmonic oscillators? We always want the period. What is the period? So remember, back from circular motion, period was how long it took something to do one full revolution. Here we don't really have a revolution. So the period is how long it takes to do one full back and forth. Okay? So basically, how long until it goes back to its starting point. Okay? So if this is your pendulum, again, the period will be the time it takes to do a full back and forth. Okay? That's your period. So not just to one side, but a full back and forth. So it doesn't actually depend on the mass, which is what's weird. A lot of people think that it does, and if you've done the pendulum lab, then you will have figured that out. And if you haven't, well, there you go. So doesn't actually depend on this mass. So what the heck does it depend on? It actually depends on the length of the cord, okay? And gravitational acceleration, which of course, well, as long as you're doing this on Earth, which I think most of the time you are, then that's not really variable. So what it really depends on is length, okay? And here is the equation for period of a pendulum. This is specifically for a pendulum, and you can only use this equation for pendulums, okay? This is on your data sheet. If you look under waves, I know you're like, what? Why is it under waves? Because we're under simple harmonic motion. Well, again, simple harmonic motion and waves are very connected, and you will find out why very soon. Well, not today, but in another lesson. So it is under waves on your data sheet. Okay, so you do get this equation. Okay, but that is for period of a pendulum. So remember, capital T tells us period. It's still in seconds, so it's specifically, though, the time for one back and forth. Okay? And that's, of course, if we're talking about a pendulum. If we were talking about circular motion, then it'd be the time for one full revolution. But basically, it's always the time it takes to before it repeats itself. Okay? Capital L is the length of a cord, so keep in mind that is capital L. Okay, we know that cases do matter, and then lowercase g is gravitational acceleration. So we'll take 2 pi, multiply it by the square root of the length of the cord divided by gravitational acceleration. And that is how we get period of a simple pendulum. Okay, so can we treat pendulums like this on Earth? Of course we can, but it's actually not perfectly harmonic. Like, we are going to lose a little bit of energy to air resistance. So even if it's less than a 20-degree angle, if you let a pendulum go for a long time, it will eventually slow down, because the period does slightly depend on amplitude. What's amplitude? That's how high you lift it. Okay. And that does decrease over time with friction. So of course, if we're looking at a pendulum in space, then none of this happens and we never have to worry about it. But pendulum down here on Earth, it is always going to lose a little bit due to friction. So this is more just a fun fact that I want to share with you. In grandfather clocks, you know, the grandfather clocks, and then they have like the big weight thingy that goes, or the big thing that goes back and forth and back and forth and back and forth underneath. So, you know, here's the clock. It's like, and then like that's in a like thing, and then in another thing beneath it, it has like that big pendulum that goes back and forth, right? It goes back and forth, goes that way and that way. And then, you know, you have like with it, like a bunch of stuff there, and yeah, it's really pretty. So the reason that this pendulum here actually keeps going back and forth and always goes back up to the same height is because it has little falling weights in it that'll like go back and forth like that. inside to counteract friction. They like have the weight to be exactly what it needs to be in order to counteract friction, which I just think is so cool. Because then it adds just like a little bit more gravitational force and it counteracts friction. So I just think that's really cool. You might not at all, but that's why grandfather clocks actually stay consistent for a really long time. They stay correct for a really long time. So that's kind of cool, I think. Anyways, fun facts. Yay. Now, we know that period and frequency are very closely tied. Why do we know that? Because we know that frequency is equal to 1 divided by the period, right? And we know that because period is equal to 1 divided by the frequency. They are inversely proportional, right? So what is frequency? Remember, that is how many revolutions per second it's making. Or in this case, how many back and forths is a pendulum doing per second, okay? And so that's what I want to know. So how many revolutions or back and forths per second? Okay, so if I want to use this equation back here to find frequency, let's do it. Okay, because I know frequency is equal to 1 divided by t. But again, what do I know t is in this situation? It's 2 pi times the square root of L over G. Okay, so that's 1 divided by 2 pi times the square root of L over G. Well, doesn't that look fun? Let's put that into two fractions there. Okay, I'm going to do 1 over 2 pi times 1 over the square root of L over G. Why am I going to do that? Because it just makes life a little bit easier. This is 2 pi times the square root of L over G. So these two things are perfectly synonymous with each other, right? 1 over 2 pi times L over G is the same as 1 over 2 pi times 1 over L over G, right? Because look, multiply those two together. What do you get? Oh my goodness, you get that, right? Why did I do that? That's because I'm going to look at this little, 1 over L over G thing there is gross. So I'm going to say, what's that? That's 1 divided by the square root of L over G. How do I divide a fraction? I flip it. Does it matter that it's underneath the square root? No, just keep it underneath the square root. Okay, so that's the same as 1 times the square root of G over L. Okay, so therefore I did that. So this can become a little bit nicer, where we can have 1 over 2 pi times the square root of G over L. Okay, is that on your data sheet? Absolutely not. So you are expected to be able to derive that equation using this equation. Okay, but that's what we get for frequency of a pendulum. So there we go. Isn't that fun looking? Okay, let's do an example of how to do stuff with pendulums. And you're going, okay, so just like 1 or 2 equations, easy. No, because we can still use everything we knew about energy before and after with this as well. So really, we're already bringing a ton of knowledge into pendulums. Okay, so let's start this. We have the length of the pendulum, 0.66 meters. The pendulum bob has a mass of 310 grams. And it's released at an angle of 12 degrees to the vertical. So we know it's less than that 20 degrees, so we are good, okay? So it says for part A, with what frequency does it vibrate? Again, it says assume simple harmonic motion, and that's just meaning ignore friction, okay? So we're gonna pretend that there's 0 friction, which is just so nice when you're doing calculations. Well, that's nice and easy because we just came up with an equation for frequency. Isn't that nice? We just figured out the frequency of a pendulum is 1 over 2 pi times the square root of G over L. Now, of course, if you don't remember this or you don't want to derive it, you could find the period first and then just do 1 divided by that answer. Of course you could. I'd be completely fine with that. Okay? So we have everything here. We just need G, which is, of course, a constant, so we always have that. And we need L, which we were given is 0.66 meters. So really, that's pretty easy for us. So frequency is 0.61. Does anybody remember the unit for frequency? It's something called hertz, okay? Hertz means per second, or 1 divided by seconds, okay? But it just, again, means how many back and forths per second. So this pendulum won't be able to do a full back and forth in 1 second. It'll only go 61% of the way, okay? So it'll go all the way over to the other side, but then it won't get quite back down to the bottom, okay? Before it gets back up to the other side at the top. So just something to keep in mind there. Okay, so that's part A. That was nice and easy. Yay. When are things that easy in physics? Almost never. So just cherish that moment for a minute. Okay, now on to B. What is the pendulum bob's speed when it passes through the lowest point of the swing? Okay, we know usually when we're talking about speed and we know stuff about energies that we're probably going to be using kinetic energy to find speed, right? So again, what do we know about energies and pendulums? We know at the lowest point, they have all kinetic energy, so kinetic energy is at its maximum. And we know at their highest point, they have all potential energy, okay? So I just need to find the potential energy at its maximum height to then be able to find the kinetic energy at its maximum, at its lowest height. Now, there is a problem here. First of all, I drew this really badly, so that's my first problem. So let's draw that a little bit better, because of course, when it's at its highest height, it's actually going to look like it's at a higher height. So then my potential energy is at its maximum there. Okay, what's another problem? Do we know how high it goes? We certainly don't, right? We're looking for this height, okay? We need that height, and we don't have it. So that's a bit of a problem, okay? So of course, when we're looking for that, we say, okay, what can we do? And the best thing is usually when we have angles to try and make a right angle triangle, right? So I know this is 12 degrees. I know this is 0.66 meters. So is this. But here's the problem, is this isn't like a nice right angle triangle if I draw it down to there, is it? Like, no, not at all. So I got to get rid of that. I want a right angle triangle because then I can use SOHCAHTOA. Okay? So how am I going to make this right angle triangle? There's only one way. I got to do this. So then it's a right angle. Then this is no longer 0.66. I don't know what that is. Okay? So what do I need to do? I need to find that height, but it won't actually give me the height of the pendulum. So think about it. If I have this nice little right angle triangle here, I can find this length, can I not? Yes, I can find that length, but so I'm going to call that L, okay? But I need the height here. So what will that be? Well, we know this whole thing is 0.66 meters. So if I can find L, I can subtract it from 0.66, and I can find my height here. Okay, so I'm going to say that once more. I can take 0.66, this whole length here, and subtract this guy from it, and then guess what you have left? You get from here to here, which is your height. Okay? The height that it's falling from, because that's going to help us get potential energy, which is mgh. So that's actually our first step here, is to find the height here. Okay? So again, how am I going to find the height? I'm going to take the length, 0.66. Minus that length there. How do I find the length? Oh, well, let's go to SOHCAHTOA. Here's my hypotenuse, my 12-degree angle. I'm looking for the adjacent side. So guess what? I'm going to multiply it by cosine of 12. Okay? So height is equal to 0.66 meters minus 0.66 meters, my hypotenuse, times the cosine of the angle that I have, since I'm looking for the adjacent side, and then I can get my height. Okay, so if I do that, I get a height of 0.014 meters. Okay, so what does that mean? It's being raised up 1.4 centimeters. Okay, or 14 millimeters. So there we go. Now I have my height, and now I can look at conservation of energy and the fact that the maximum potential energy will all convert itself into the maximum kinetic energy. Okay, so let's go on to the next page to do that. So this is still part B. It's just part B continued. So of course we know the sum of all the energies initially should equal to the sum of all the energies finally. Okay, so we'll make our initial point our highest point, and then we'll make the final point the lowest point, where it's all kinetic energy. Okay, so the mgh at that initial point should all equal to 1/2 mv squared at that final point, because again, we are looking for velocity at the lowest point of the swing, and at that point there's only kinetic energy, but at the highest point of its in its motion, it's all potential energy. So we know all potential is being converted into kinetic. Okay, so let's solve for velocity here. First of all, I see that I have mass on both sides, so I can cancel those out. And then I get velocity is equal to the square root of 2gh. Okay, and of course we found the height that it's falling from. And of course g is just 9.81 meters per second squared. So it's simple once you get here, but it's a little bit difficult to get here. Okay, there's just a lot of math in order to get that height. Okay, so what I get for velocity, I get 0.53 meters per second. And that is its speed at the lowest point of its bob, so that'll be its maximum speed as well. Okay, there was one more part of this, so let's take a look at what it's asking us. So what is the total energy stored in this oscillation, assuming there are no losses? Okay, so remember, total energy, it's kind of talking about mechanical energy, okay? Because we know it's just going back and forth from potential, which is mgh, plus kinetic energy, which is 1/2. Oh, I just put kx squared. Of course, that's for a spring, which is definitely not what we have here, mv squared. Okay, and this is at any point in its motion. Okay, so at any point in its motion. So what would be a smart point to choose? I would say there's 2 points at which would be the smartest. I'd say at either its lowest point or its highest point. Why? Because it's at its lowest point, what's the only kind of energy it has? Total energy or mechanical energy is equal to, here's when it has maximum kinetic, but does it have any gravitational potential? No, because h is 0. Okay, so I'd either choose the lowest point, or, this is obviously exaggerated, I would choose the highest point, because what is the total mechanical energy at this point? Again, it's still 1/2 mv squared plus mgh, but what's my velocity right here? It's 0, so we don't have any kinetic energy right there. So I would choose one of those situations to find your total energy, okay? Because we have its highest height, we have its fastest velocity, so either one of those is going to get us where we want to go, okay? So let's choose that one. Let's choose when it's at its highest height. So mechanical energy should equal to, and this is the same as total energy, so mechanical energy should equal to just mgh, okay? And that's, of course, height when it's at its maximum, which we found to be 0.014 meters. So that works really well for us, okay? So that's all we're going to do. And what was the mass again? It was 310 grams. Remember, we need that in kilograms, so that is 0.310 kilograms. times g, 9.81 meters per second, times the height, which was 0.014 meters. Okay, so my mechanical energy totally is 0.044 joules. Okay, so there we go. And that's that. So I'm sorry to tell you, you can't forget everything about work and energy because it's all coming into this unit. We're going to be using lots of stuff to do with energy. Okay, but that's the period of pendulum. Stay tuned for simple harmonic motion.